Mine's 17. All right. Hello, everybody. Welcome back to Comp 3430 Operating Systems. I hope you are all doing okay. The pace of questions around the assignment has dramatically increased starting on Wednesday, which is really good. I'm happy to see that people are asking questions fairly early in terms of like the assignment's not actually due until next week. So I'm really happy that people are getting started and working on it early. I hope that this isn't the only thing you're spending your entire weekend doing. I hope that you have some other plans to get out and do something. I'm planning to go and see a movie with my kids tomorrow that's called Dogman. I don't know if you've seen ads for this movie or if you've read the graphic novels of Dogman. Maybe you're too old to have read them. Yeah. You read Captain Underpants? Okay, so it's the same author that does Captain Underpants. And for the uninitiated in terms of Dogman, Dogman is this story of a dog-headed cop whose origin story is pretty much that a police officer and his dog got into a big accident, and they had to go to the hospital, and they couldn't save the cop's head, and they couldn't save the dog's body. And the nurse lady, and I'm not just saying nurse lady for any reason, that's literally what the character's name is nurse lady. She comes up with the great idea to put the dog's head on the cop's body, and thus is born Dogman. And there's a bunch of like crazy antics adventures. I really like these books. This is a completely unrelatable story. I realize I really like these books because they are just filled with like absurd humor. So they're good kids books, but like I'm an adult reading them to my children, and I think they're pretty funny because of the absurdity of what's going on. One of the storylines, and I'm really digressing here, but one of the storylines involves different sprays that have been invented. One of them is called living spray, and it causes the inanimate objects to become alive when you spray them. And so it eventually turns into this whole sequence where the downtown buildings have been brought to life, and they've got these massive muscly arms, and they're villains in this thing. And yeah, someday maybe you'll read this on your own. Maybe not, probably not. Let's talk about operating systems. So what I want you to be able to do by the end of today's lecture is very similar to what we had last time. And so I'm just going to skip through all of these right away. The main thing that I want to add to this here is that last class, at the very end of class, we kind of feverishly started trying to work on using the wait system call. And it kind of got messed up because as I was going through the process of trying to work with this wait system call, I eventually realized that I was in two different directories that had the same files in them. And so I'd made changes to one and was compiling it, and it wasn't actually having the effect I was expecting it to have because I wasn't actually looking at the right directory. So I'd like to fix that today. I want us to take a look at the wait family of system calls. And I want us to take a look at the exec family of system calls. They accomplish different tasks, but they're going to kind of complete the management of processes for us in terms of what we're going to need to be able to do in terms of managing and manipulating the life cycle of a process and managing and manipulating the kinds of things that the operating system does with processes. It is Friday today, and so I do want to spend some time taking a look ahead at what we're going to be doing next week. And so I'm going to pop over here to next week's section. I'm going to make some announcements about the assignment a little bit later in class today. But we're looking at week 6 now. We are getting to the halfway point in the term. One of the things that we're going to find out today, sorta, is that once our processes have forked, once we've created this new process, there's not an obvious, meaningful way for these different processes to then actually talk to each other again. It's kind of a one-way thing. You cause a process to start, and then it's off on its own. And what we're going to see today is that we can at least sort of synchronize things when they're happening. We can make the parent process wait for its child process to finish, but they can't talk to each other. They can't let each other know that something has happened. They can't send messages back and forth to each other. And so we're going to spend some time taking a look at interprocess communication. And really specifically, we're going to look at these two different approaches to interprocess communication called pipes and signals. Pipes and signals do different things, but they both allow us to have processes that are related. So in the case of fork, and also unrelated processes to communicate with each other. So processes that don't have a common parent to talk to each other. The readings this week are different. I'm going to say it that way. The readings for this week are different. Operating Systems 3 Easy Pieces does not cover interprocess communication at all. I personally find this to be something that's lacking in this textbook. While I think it is a great textbook, it does miss this part of processes. And so what I have done is drawn from a different textbook. And that different textbook is called Advanced Programming in the Unix Environment. I am looking for you to read sections of this chapter 15. This is a book that is not free, but I have had the library scan this chapter for us, and it's available on the course website alongside the course material for week 6. So you can find a PDF copy of it there. There are only 4 sections. You're going to open the PDF file and see that it has 58 pages in it. Please don't panic as soon as you see 58 pages, because I don't want you to read 58 pages of stuff. I'm not interested in that. There's stuff that's way outside the scope of this course. I only want you to look at the introduction, the section on pipes, the section on P-open and P-close, and this section on FIFOs. I'm even going to walk this back and suggest that you don't read this chapter at all, and instead just watch the video that I've made that describes this chapter. Use this chapter as a reference, but spend more time with the video than you would with the textbook chapter, because I give a little bit more comprehensive overview of signals in the video, where there is nothing about signals in this textbook chapter. It's a good reference. It has some good examples of code that you can write that will work with pipes, and it has some good example of code that you can use with FIFOs, but it doesn't talk about signals at all. And so my strong recommendation for you in terms of preparing for next week's class is to watch the video and not to read the textbook chapter, but to keep that in your back pocket as a reference for the kinds of code that you might expect to see for working with pipes and FIFOs. I've also listed here 7 manual pages. These are for your reference. I'm giving you a pointer to these manual pages because these are functions that you're going to have to use eventually when you're working on your next assignment. But they're not really meaningful to just read in isolation. They're not valuable to just sit down and read the manual page for kill. That's not good, relaxing reading. It's valuable when you need to use the kill system call, but it's not super valuable to just sit down and read this thing on its own in isolation. All these manual pages are pretty good in terms of their content, and a lot of them will have examples at the bottom of the manual. This one here at the very top kind of stands out, this man7 signal, or each of these are links to an online manual copy, so you don't have to open up a terminal to look at this. Section 7 of the manual pages describes concepts. So section 7 here for signal is not like how to use the signal system call. It's telling you about what signals are and how they work overall in Linux and Unix systems. It's a good resource to have available, but it's not something that I insist that you read. Likewise, all of these section 2 and 3 manual pages, they're valuable for when you're working on your assignment, but they're not necessarily going to be valuable in terms of like, I need you to read this right now. So that's where we're going for next week, and again, emphasis on watch this video as opposed to reading specific sections from this chapter. That's my strong advice to you about this. The other thing that you notice about week 6 is that we have a term test scheduled on Friday next week. We've got a term test scheduled on Friday next week. And so I want to spend a little bit of time telling you about what to expect on the term test. I'm going to promise that I will make some time for questions about the term test next Wednesday. That will be the last time we see each other before the test. And then hopefully it will be less of a feverish focus on assignment 1 and a little bit more mind share for what we're looking at on the term test. But to give you some idea of what we're looking at for the term test, the first point I want to make is that I'm not going to ask you to do programming in C on this test. I strongly believe that I have adequately asked you to do C programming on your assignment. I believe that you have accomplished that goal on your assignment. I don't need to see that you can do C programming on a written test. You might expect to be given some C code, like I might give you a listing of a program, but I'm not going to ask you to write any C code on this thing. The strong emphasis that you should be looking for in terms of the course material is the learning outcomes that I've stated in the course schedule. So every week I've gone through this process of trying to describe the kinds of things that you should be able to do, and every class I'm trying to say the same sorts of things. These are the things that you should be able to do, and this is what I'm going to be assessing you on ultimately. You should be looking at the learning outcomes for emphasis on what you should be expecting to be assessed on, and the material that you're going to be assessed on is up to and including week 6, with very little emphasis on week 6, because you'll have had about 72 hours to actually think about this stuff. So there will be some things on interprocess communication on this test, but that will be a very limited part of the test, a very, very small part of the test. In terms of learning outcomes, the other thing I think I want to say about this is that when I've been doing the learning outcomes, I'm trying to attach these to specific activities and exercises that we're doing in class. And in terms of the activities and exercises that we've done in class, those are good indicators of what I'm going to ask you on the test and how I'm going to ask you those kinds of questions on the test. The last thing I want to say about the term test is that seating is going to be assigned. So I will be sending you an email on Thursday of next week to tell you what seat you are supposed to sit in. You must write the test in the section that you're registered in. I'm also going to be printing your names on the test. So your names will be pre-printed on the test before you arrive. I'm going to tell you what seat to sit in by email. I'm going to post on the course webpage an approximate map of this room that says this is where seat 1 is and this is where seat 70 whatever is, so you have a sense of what the room overall looks like in terms of finding your test when you get to class. But you must write the test that has your name on it, and so you must come to the section that you're registered in to write the test. If you've made arrangements to write your test in a location that's not our classroom for accessibility services purposes, the test that has your name on it will be given to accessibility services. So you will get the test that has your name on it if you're not writing your test in this classroom. Please bring some photo ID. I strongly prefer that you bring your student card, but any photo ID is fine. So a driver's license or a passport are also acceptable pieces of photo ID. I'm not going to have questions right now about the test. Like I said, I'll save some questions for Wednesday next week. But in general, if you want to ask questions about the test, my strong preference is that you do this on the course forum or in class next week so that students in the class all have the same information. I don't want to have a situation where someone has come to my office hours to ask a question about the test and I unintentionally give them some special information about the test. I want to make sure everything's fair for everybody. All right, okay. So let's talk about managing processes. What we've got so far is we have been able to create new processes using this fork call, but I also want us to be able to manage and synchronize processes. So we're going to take a look at the following. I want to take a look at the wait family of functions. These functions are going to be used to have processes waiting for each other. a parent process will be able to wait until a child process has finished or terminated or exited before it continues doing anything else. That's the first thing I want to take a look at. How wait changes the state of a process. So this is a blocking system call that we're making. So we're going to stop execution in our parent process until some event is happening in our child process. And then finally, I want to take a look at the exec family of functions. The exec family of functions are kind of as weird and mind-blowing as the idea of fork is, in terms of something unexpected is going to happen and we are going to lose control of the process that we created when we call this function. But we'll take a look at that when we get to that point. I'm going to pop over here to my terminal. What I've got here is, this is the process management code. The repository that I posted up on the course webpage, and I haven't updated it, so if you don't have this on your system already, you can clone this repository, but we're kind of starting from the initial state that I had posted up on the repository the last time I made a post about it. We're going to be taking a look specifically at this process management code. So I'll quickly remind you of what's here. We've got this just accept it. It's different. It's not the same as what we've seen in our main function before, but we're going to gospel put this in right now. We're including this NP array of things here. We're not using these in our code, so we're casting them to void. We've got this variable called PID. This is the process ID that we're ultimately going to get back from the forks function. We've declared this stack allocated variable called letter, and we've put a value into it. We've printed something, and then down here is the really interesting part, where we do the fork. So on line 27, we're calling this fork function, and we're asking the operating system to duplicate our process control block. This makes it kind of look like we now have it literally is two processes now running the same code, but the mechanism that's happening underneath this is operating system is like doing memcopy, basically. I've got this structure that represents the running process. I'm going to do memcopy on that, and I'm going to change the value of the registers that we have in this process control block for the duplicate and the main one that I've made, so that the value that gets moved into this memory location for the variable that we're assigning back to is going to be different for each of those different processes that are running. Once we have these different values, then we're going to inspect the value. The value that is always going to be put into the child process is 0. It will always be 0 in the child process. In practice, when we run this code, the child process will always have 0 injected into it. That will be the value that comes back from fork. In the parent process, what we get back is the process ID of the new process that was created. So this is my duplicate. This is the ID of my duplicate so that I can use this for the purposes that I need to use it for. Within this conditional statement, once we leave that fork call, now we're kind of continuing in both of these processes at the same time, but only that child is going to be the one that enters this conditional statement, because only the child is the one that has PID equal to 0 coming back from the fork function. And so here what we're doing is we're printing out another print statement that gets its process ID, but then also we're changing the value of this variable to clearly demonstrate that the address space for the parent and the address space from the child are separate from each other. So I can make changes to a variable in my child process, and it does not change that variable in my parent process. We duplicated the PCB. We've copied the contents of memory. Big, big air quotes around this. We've copied the contents of memory. We haven't literally copied the contents of memory, but for the abstract purpose of what we're doing right now, we have copied the contents of memory into our other process. And then at this point on line 43, we've caused them both to block on standard input by calling getchar. When we ran this code, we have to press enter 2 times here, because there is only one terminal that these processes are both attached to. So I press enter once, and one of them wins and is able to finish and get unblocked. I press enter again, and the other one is able to finish and unblock. They're both sharing the same terminal, and then we're both exiting at this point, and our OS is kind of cleaning up after us. What I want to do now is I want to spend some time taking a look at the relationship between these two processes in terms of what's happening as they're running and exiting. So if you've got this code on your system, I invite you to code along with me. What I'm going to do here is, in my child process, I'm going to move the block that we have, so the call to get char, I'm going to move it into this conditional statement. My goal here is that I want only the child process to block. I don't want the parent process to block. I only want the child process to block. So I'm going to cut this code. So I'm going to highlight these lines and cut them and paste it over here, and then I'm going to highlight these lines and indent them a little bit so that they're clearly inside of this conditional statement. I'm going to compile this code, and I'm in the correct directory this time. I checked before I got to class today, and we're going to run it. So I'm going to run process management, and what I'm going to do is I'm going to open another terminal to the side here so I can inspect the output of PS here. I want to be able to see what processes are running right now. The last time we ran this, where both of them are hitting this get char statement, we could see two processes running. And that was our goal. We wanted to duplicate this process and see that two processes were running. I'm going to hit enter here. And what we're going to see as output now is that there is one process still running. If I hit enter on my keyboard here, and I run PS again, now we have no processes running. So let's step through this. I don't normally use Vim splits like this, so I've printed a cheat sheet here for myself. This is how I learn new features. I've been using Vim for a long time, and I've never actually really spent a lot of time using this feature. So please forgive me if I flail a little bit here. But what I want to do is I want to go to the top of each of these buffers that I've got. And I'm going to say that on the left side here is our parent process. This is the one that begins to run immediately. So it's going to start executing code, and I'm just going to step over these lines. We're going to print f hello world. We're going to keep continuing along here until we get to this fork statement here. Once we hit the fork statement, I'm going to scroll quickly down to the fork statement here as well, and we're going to say that on the right side is our duplicate process. This is the one that gets duplicated. Once we hit the fork statement, we're going to have both of these processes starting to run. The parent process is going to go down here and get to this if PID is equal to 0, and the child process is going to go down here and get to the same conditional statement. In this case, the child has 0 in that PID variable, so it's going to enter this conditional statement, and then it's going to get stuck here. It's going to block until I press enter on my keyboard. The parent process is just going to skip past this conditional statement because the value that it has for PID doesn't allow it to enter this. It has the process ID of the child process in that variable. And so the parent just kind of keeps on trucking and exits. And the child process is now kind of just stuck, waiting around for me to press enter on my keyboard. When I hit enter on my keyboard, we unblock this process, and then it's allowed to continue and kind of finish after that. But that's not ideal behavior. That's not the kind of behavior that I really want to see, because what I want to do is I want my child process to kind of do something for me, something that's different than what my parent process is doing. And so what I'm going to do is I'm going to add a little bit of code here that's going to change the behavior of what our parent process is doing. I want my parent process to be a responsible parent and wait for its child to finish doing whatever it's doing. instead of just abandoning it and like leaving it to run in the system. There's a family of functions that we're going to be taking a look at to do that. I'm going to come back to this code in just a second. The family of functions that we're going to be using are the wait family of functions. There is a function that's called just wait. There's a function that's called wait PID, and there's another one that's called wait ID. We're going to be looking specifically at wait PID right now. I want to be able to wait for a specific process to finish executing. More generally, what I'm doing here is waiting for a specific process to change its state to finished. So not just finish necessarily, but actually change its state to finish. Wait PID takes 3 arguments. The first one is the process ID. This is the process that I want to wait around for. The second is annotated here as a pointer to a nullable integer. And what that tells me is that I can pass null to this if I want, and it's not going to crash. I could pass a non-null integer pointer to this. And what it's going to do is it will put the status of the exiting process into this variable. So remember, at the bottom of every program so far that we've written, it says return exit success. Exit success is going to get stuffed into this variable if we have put a pointer to something here. Options are something that we're not actually going to spend too much time dwelling on right now, but we can change the behavior of what we're waiting for if we want to. We're going to pass a hard-coded value of 0 to this because we just want to wait for this exit event to happen. So I'm going to zoom out of here. And what I need to do with this is I'm going to have to go to the top of my code and add a new include sys/wait.h. And then I'm going to go back to my else statement, and I'm going to start waiting for this thing to happen. So I'm going to put wait PID. The process that I want to wait for is my child process. So I'm going to put PID here. I don't care to inspect its status when it's done. I'm happy to have just waited for this child to finish before I proceed doing anything. And like I said, I'm going to hard code a value of 0 here for options. I don't care how it exited. I don't care to stop on different conditions. I just want it to stop. I want to block until this process has exited. So what this says is block until the process with PID has exited. That's the state that we're in right now. So I'm going to save this, and I'm going to quit my manual page, and I'm going to make this again, and I'm going to run it. Now, what we've got is 2 processes running right now. They're both sleeping, they're both blocked. The way that this works, I'm going to do the same thing. So the left side is my parent process, and the right side is my child process. I'm going to bring them both back up here to fork. So we're both sitting on fork right now. We're both about to return from this fork statement. The child process returns. It gets to this conditional statement, and it inspects the state of the value PID. The parent process returns. It inspects the value of this PID variable. My parent process is going to go to the else part of this. It's going to go to the else part of this because the value of PID is the process ID of the child process, the duplicate. My child process is going to begin to execute the first branch of this conditional statement because the value it got back from fork is 0. It's going to start executing, and it's going to get blocked on line 43 here on getchar. So it's just stuck. It's waiting for me to press enter in my terminal right now. My parent process over here is on line 49, and now it is also blocked. It is stuck because my child process, the process that has the value of PID here, has not exited. So we're just like, in both processes, we're stuck. We are blocked. I'm going to go back down to my terminal here, and I'm going to hit enter. And I'm going to go back over here to my other terminal, and I'll hit PS, and now there are no processes running anymore. So what's happened here is, in my child process, I hit enter. Nothing is happening in the parent process yet. My parent process on this wait PID line on line 49 blocks until the process has exited. So it's not going to do anything until the process is exited. I hit enter on my keyboard, and now the child process is going to continue exiting. The PID returned from fork is 0, the value of letter is C. And then it exits. And only then is the parent allowed to proceed. After this return exit success happens, then my parent is allowed to continue. And it prints out the value of PID returned from fork is whatever, 27 something. The value of letter is W still, because my parent doesn't have the same address space as this child process. And then it also will exit. This gives us some important properties. The first is that we were not able to guarantee before which process would get to print first. If I comment out both of these lines, and I just allow both processes to continue to completion after the fork statement, I cannot predict which one will print out first. It will look random, it will change every time I run this code. When I put these blocking statements back in, now I can predict and confidently say that the parent will not execute these lines of code. It will not print these messages out until after the child has exited. It cannot proceed past that wait statement until the child has exited. This is the idea of synchronization. We are beginning to synchronize these two processes. We're forcing one process to stop doing stuff until another process has actually finished. Yeah?
If we wanted to get the child to wait for the parent, we would just be able to make a variable before the fork that has the parent process in it with get PID.
Yeah.
And then do the opposite, right?
So I'm going to do exactly what you're suggesting here to make sure that we're talking about the same thing. I'll call this parent PID. And just for the fork, I'm going to say parent PID is equal to get PID. So this is only executing before we've done the fork in the first place. And then in my conditional statement here, I'm going to change this to not get char, and I'm going to comment this out as well. And I'm going to put here wait PID, parent PID null 0. And I'll put the get char in this one. So this is going to be the parent is blocking. The parent is blocking on keyboard entry on standard input, and the child is blocking until its parent process has exited. That describes what your thought was? Okay. So I'm going to go down here, I'm going to make it, and I'm going to run it. And we've got something slightly different here. We've got this defunct zombie process. We've got a defunct zombie process because our parent has potentially exited before our child has finished, potentially. But the behavior I think that you were expecting is what's happened here. The parent is able to complete after I press enter, and then only then is the child able to finish executing. Typically, you don't do it that way, though. Typically, it's the other way around. The parent always waits for its children to finish up. Yeah. I'm going to undo all this stuff because I want it to be back in the state where we've got the correct ordering of things. Yeah.
For wait, what kind of, like, is it using some sort of polling, or is it using like an interrupt to determine when to check?
So that's a good question. The question is wait using some kind of polling or interrupting? The mechanism that it's actually using is in the operating system side. And the operating system is going to look at what that process has asked it to do. So our parent process over here has asked to wait for a specific other process to exit. And so our operating system is then able to say, this process shouldn't even be scheduled until that event has actually happened. So it's not really polling on the part of the process. The process is just effectively going to shut down, and it's not going to be able to run until the operating system will not allow it to run until that event has taken place. The operating system may be doing some kind of polling internally, but more likely it's just going to choose not to schedule that process when it's making decisions about which process to schedule, which we will talk about much later in the course. But it's just going to say, I'm not going to let this one run because it's not going to be able to run. Yeah. All right. The main difference between wait, PID, and wait, just to be clear, is that wait will wait for any child process. Wait PID waits for a specific child process. So when we fork multiple children from the same parent, which is a normal thing to want to do, when we fork multiple children from a parent, wait will just wait for any of them to exit. Wait PID will explicitly wait for a specific process to exit. Sometimes you want to wait for any child to end, and sometimes you want to wait for a specific child to end. Wait PID can be implemented with wait in general can be implemented with wait PID if you take a look at the manual page and you pass a special value for PID. But generally the difference is wait for any child or wait for a specific child to finish. All right, the very last thing that I want to do here is I'd like to change this a little bit more. And what I want to do is visit the exec family of functions. So I'm going to come back down here to my terminal, and I'm going to open up the manual page for exec. And there are a lot of different exec functions that we can call. The one that we're specifically going to look at right now is the one that's called exec VP, but we will also be using this exec VPE version of this thing. They all ultimately accomplish the same thing. At a very high level, this is a function or system call that is asking the operating system to replace the code, stack, and heap section with something else. It's replacing the code section with the program that you want to start. It's replacing the heap with maybe zeros, but it may be doing nothing. And it's replacing the stack with ultimately the main function stack as an entry point for this new program that we're going to run. So I'm going to close this. I'm going to go back to my code here, and I'm going to go to the top, and I've got UniSTD already included. This is the header that we need to include. And I'm going to do this in kind of a dumb way. I'm going to do this in a way that I'm just hard coding something to happen because I just want to use the call right now. That's all I want to be able to accomplish. What I'm going to do is in my child fork of this, I don't want to get char. Instead, what I'm going to do is I want to call exec VP. Exec VP takes two arguments. It takes the name of the program that you want to run as a string, and then it takes the array that becomes the argv array in this new program that you are working with. So what I'm going to do here is I'm going to manipulate our own argv array so that I can pass it to exec VP. I'm going to say that argv at entry 0 is equal to cat. Cat is a command line program that you can use to print stuff out. That's what it does. Cat is not just what we have in the assignment, but it's also like it's its own thing. It's its own thing that we have on the command line to be able to print out the contents of a file. argv at 1 is going to be the first argument that would be put on the command line for cat. And so what I'm going to ask cat to print out is this program's source code. I want it to just print out the source code that we have for this program. The argv array is a null terminated array. So in argv3, I'm going to say null. This is the last argument. You shouldn't pass anything more. You shouldn't consider anything more that's been passed to this thing. So argv is a null terminated array. What we pass to exec VP is going to be, I'm going to pass it argv0, but you could pass it cat in strings here if you wanted, and then I'm going to pass it argv. I'm going to print out after that, I am still running code in the child process. And then I'm also going to print out sad face, not really. I'll never see this line printed out at all. When we call exec VP, what we are saying is, please take this program and replace my code section with this program. Take all of the assembly language instructions in cat and stuff it into the code section of my address space. Change the stack so that it points to the entry point for that program. Change the heap so that maybe reinitialize it, maybe do nothing, but change the heap so that it's something else. If exec VP works correctly, it will never return back to our code. It doesn't know about our code. It's never able to come back to our code. And so these lines of code should never print. These should never, ever print. I'm going to save this. I'm going to go back down here, and I'm going to expand this for now. I'm going to make it, and I'm going to run this again, because these are just going to terminate immediately. They will just run and terminate immediately, because cat is not going to block on anything here. It's just going to read the contents of that C program and finish. So when I hit enter on my keyboard, it prints out the contents of this C program, because I've passed the name of this file to cat. I've basically run this. I've run that program. And then it prints out the PID returned from fork is this, the value of letter is W, because this is the parent process finishing. It waited for cat to finish, and now the parent process is allowed to unblock and finish and do what it needs to do. But those two messages that we put after the exec VP call never run, because we never come back to this code to be able to do that. We've completely replaced the code segment of our address space with the code segment for this other program. I'm going to commit this to the Git repository, and I'll push it. So if you want to get a copy of this, you should pull it. I'll also make sure to try and link to this repository under today's lecture notes so that you can be reminded of its address. I'll leave time for questions about this next week, but I want to spend a little bit of time with questions and kind of statements about the assignment. The first thing I want to point out to you about the assignment is that I've posted this announcement on the course webpage. I've added two additional programs to the repository. One of them is called ls.c and the other one's called paste.c. ls.c is a program that calls the getDents function. To give you an idea of how that's going to be called, ls.c should list the contents of a directory. It does the same general idea as what we're doing with ls on the command line, except it's going to be paths that are inside the volume that you're working with. Paste.c, like I said last time, it takes two file arguments and it just sticks them beside each other. So it prints out the line from one, and then the line from the next one, and then a new line character, and then the line from one, and then the line from the next one, and then a new line character. I've updated the README document to tell you how to compile and use these programs, but if you've got nqp exfat.c, it's make, and then you can run them. There's instructions about how you can run the programs. I've also changed the functions comment for nqp getDents to better explain what I want from this function and to change the expected value for the count here. What I'm expecting for this is I want you to pass the number of directory entries in this header that I want to get back. So I'm going to quickly look here at both ls.c and nqp io.h. So in nqpio.h, what I've changed here in getDents here is I want you to pass a count here that represents the number of the structures that I want you to read. The type of structure that I am asking to be read is this structure here. Not the directory entries in exfat, it's that structure there. So if I pass 1 to this, I'm going to be passing you enough space for one of these things. The job that nqp getDents or getDents, I'll affectionately call it getDents, is to take directory entries from our exfat system and translate them into this. ls.c then is going to use that getDents function. It's initialized this entry here up at the top. It's of type nqp_dirent, and it's printing out the name and inode number that we get back from this thing. Within your implementation of getDents, you're going to have to dynamically allocate the string for the name, so you'll have to call malloc, and it's the caller's responsibility, this code, to call free on that thing. So you don't have to worry about providing a destructor for this type. We're explicitly saying you know what the contents of this are, it's your job to free it, and so it's freed here. The other thing that I've done with the assignment is I've changed one of the two things that I posted last time for the volume, the 2-file root. The initial version of this that I posted had these 2 files as Unicode encoded text files, which made it look real weird if you started to work with these with your code and you were working with bytes. There were a bunch of extra bytes that were actually quote characters. So a single quote character would take 3 bytes instead of just being one thing. And so I've changed this to be ASCII encoded, and I've changed this to make sure that the line endings are Unix line endings. So they're not carriage return and new line, it's just the new line character. The README has been updated to explain how I have changed the content of that. And with that, what I would like to do is I'd like to find out if you have any questions about the assignment in the last couple of minutes of class here. So I'll give you 30 seconds to do this. And then I'm going to flip over to the Mentimeter, and it should have the code up on it. You can also ask verbally if you want. This isn't a requirement to use Mentimeter. That's a good question. What do you think is better to implement first, getDents or read function? So the first part of this answer is not about read at all, but it's about open. At least for the way that I implemented this, after I implemented the open function, I had effectively completed the getDents function as well, because I have to do basically the same things to do open as I have to do with getDents. And that is, I've got to read directory entries to find out what my entry sets are as I'm traversing the folder structure. The read function compared to getDents, in terms of like initial implementation, the initial implementation of this really ought to be, and I really suggest that you structure your implementation this way if you haven't already, begin working with files that fit within a single cluster. If you're working with a file that fits within a single cluster, the read function is straightforward to implement because you don't have to worry about switching between clusters at any point. You can fully operate within the scope of a single cluster. It's when you get to the point of having to decide whether or not you need to like move to the next cluster and then also determining which is the next cluster that makes that become more complicated. So I guess I'd answer this to say if you've already done open, then getDents should be straightforward, and you could go to that. The read function is also straightforward, but kind of like starting from the basic part. I found that long file name has an incomplete fat table that I can't read all the data from. So in some cases, this file this file's root directory should fit within the first cluster of the root directory because there's only one file in this thing. The actual file itself will probably have the no fat chain bit set on it, so it's not going to have a valid cluster chain. When that no fat chain bit is set, the cluster chain is not guaranteed to be valid at all. It may have something that's kind of like suddenly terminating, or it may have a value like 0 in it to indicate that it's going back to some other non-valid cluster. So that might be what you're seeing here, is that you have to take a look at that no fat chain bit. What should I expect to see when I read picture.jpg? So in the README for the volume, I put a link to the picture that I actually put in there. It's a smaller version of it, but it's like this abstract picture from the 1700s, from the 18th century. There's also an example of what, but there's a link to it for you to see. I'm going to do one more question, which is that one. It's the same thing? Okay, it's the same thing. All right. I'm sorry that this is truncated, but at this point, you should be able to write code that manages processes, and you should be able to describe the life cycle of a process, and then generally describe how the operating system manages processes. I hope that you all have a great weekend, and I will see you next week. Bye, everybody.